So is microjitter completely ruining your multi-axis precision? I mean, think about it. In high-speed automation, a single microsecond of lag can literally cause a catastrophic mechanical failure. When you're trying to orchestrate complex robotics, synchronizing nanosecond precision telegrams across distributed clocks isn't just a nice-to-have. It is absolutely everything if you want to eliminate that jitter.
If you've ever dealt with standard Ethernet and high-speed automation, you've probably hit that wall. Its fatal flaw: unpredictable latency. Standard Ethernet relies on collision detection and these really bulky TCP/IP protocol stacks, which basically means your messages can and will get delayed. And in a modern factory, that tiny delay is the difference between a perfectly machined part and a devastating hardware crash. Standard Ethernet simply fails when nanosecond-level synchronization is required. But today, we're setting up EtherCAT as the definitive solution to that exact problem.
Hi, I am Cat017, and welcome to The Explainer. Today, we're diving deep into the digital architecture of real-time communication. We'll be exploring industrial Ethernet mastery, and you'll see exactly how real-time determinism completely transforms motion control.
Here's our roadmap for today. We're going to cover the microjitter problem, the functional principle of processing on the fly, distributed clocks, cyclic versus acyclic data, physical diagnostics, and finally how all of this creates perfect multi-axis harmony. All right, let's just jump right into it.
Section 1, the microjitter problem. Let's look at exactly why standard Ethernet fails us in motion control.
The critical issue with standard Ethernet is really a hardware-level bottleneck. Master controllers have to send out individual requests to every single drive, and then sit there and wait for individual responses. Doing it that way makes nanosecond-level synchronization physically impossible for multi-axis robotics. It relies entirely on these unpredictable individual cycles. EtherCAT, on the other hand, is perfectly deterministic. It uses a totally paradigm-shifting method where a single frame processes data for all drives instantly. We're going to see exactly how this totally eliminates those communication bottlenecks.
Section 2, the magic of processing on the fly. Let's take a peek inside the frame itself.
So instead of relying on a microprocessor to chew through bulky TCP/IP stacks, EtherCAT uses an EtherCAT processing unit that functions entirely in hardware. Inside the standard IEEE 802.3 Ethernet data payload, we have one or more EtherCAT datagrams. Each datagram contains a header, the data payload itself, and a 16-bit working counter right at the end. This whole structure is optimized for maximum throughput. It allows the master device to send a single telegram that passes through each and every node on the entire network.
Think of the frame's journey kind of like a high-speed roundabout. Step 1, the frame enters the EtherCAT slave controller, or ESC, through port 0. Step 2, as the frame passes through the processing unit, the node reads the data addressed to it and writes its response back into the frame on the fly, like instantly. Step 3, the frame moves downstream to port 1. There's no waiting, no storing the frame in memory. It's delayed only by the physical hardware propagation times. Remember that working counter we just mentioned? This is absolutely crucial. That working counter is incremented in hardware by every single slave that interacts with that datagram. When the frame eventually loops back to the master checks this counter. If the number isn't exactly what it expected, the master instantly knows there's a problem somewhere in the network. It's literally an incredibly elegant way to ensure flawless data exchange.
Section 3, mastering distributed clocks and nanosecond alignment.
Now, fast frames alone just aren't enough, right? We need an impeccable timing foundation to trigger simultaneous movements across a massive factory floor. Instead of trying to force perfectly synchronous communication, which totally falls apart the moment there's a tiny network delay, EtherCAT uses a distributed clock system. A reference clock, which is typically the first device right after the master, orchestrates the synchronization across all the subordinate ordinary clocks in the network. Here is the exact three-step sequence the system uses to guarantee that synchronization. First, the master sends a frame to measure the physical propagation delay between all the local clocks. Second, it compares the local times against the reference clock and compensates for the offset. Finally, it regularly corrects any drift between the local system times and the reference clock, and doing this entirely eliminates communication jitter.
And what's the result of that three-step process? A staggering 10 nanosecond resolution. 10 nanoseconds. EtherCAT can link local time to measured values with up to 10 nanoseconds of precision. This is a real game changer for motion controllers, because when you calculate velocity from sequentially measured positions, even a microscopic timing jitter creates massive velocity spikes. But with 10 nanosecond precision, your velocity calculations are absolutely flawless.
Section 4, cyclic versus acyclic data exchange mechanics.
So we've got the speed and we've got the timing. Now, how does the network juggle different memory demands? Well, we essentially have two streams of data coexisting. First, process data objects, or PDOs, handle the cyclic data. This is your continuous, rapid-fire, high-speed exchange of urgent position and velocity commands. On the flip side, the mailbox protocol handles acyclic data. This is for your non-urgent parameter settings and diagnostic messaging, and it uses a careful handshake mechanism so it never ever interrupts the high-speed motion cycle.
To manage all this high-speed cyclic data, EtherCAT employs a brilliant piece of engineering called 3-buffer mode. Inside the EtherCAT slave controller, there are 3 distinct memory blocks managed by the sync manager. This ensures the producer of the data and the consumer of the data never accidentally overwrite each other's live memory.
Here's how that buffer swapping process actually works line by line.
The producer, say the master, writes data into the first buffer. Once writing is done, that buffer is locked tight to maintain data consistency. Meanwhile, the consumer, the local microcontroller, is reading from a completely separate third buffer. Once both are finished, the sync manager swaps the buffers. This guarantees the receiver always gets the latest consistent data without any delay to the main network cycle.
Section 5. Physical diagnostics and optimizing the layer.
Let's shift our focus down to the actual physical wire itself. High switching frequencies in modern 2026 robotics can wreak total havoc on signal integrity. To combat this, the EtherCAT slave controller has rigorous diagnostic telemetry built right into the hardware. Every moving frame is checked with a 32-bit CRC checksum, featuring a minimum Hamming distance of 4 to reliably detect bit faults. Because each node checks the frame on the fly, the system provides exact fault localization. It automatically detects gradual cable degradation, interference, or defective connectors way before they cause a catastrophic system failure.
And speaking of the physical layer, the topology flexibility is just incredible. Because EtherCAT operates as a logical ring, processing frames like a roundabout, you can achieve a fail-safe, redundant ring network instantly. All you have to do is route a standard Ethernet cable from your very last node back into the master's second port. If a cable breaks anywhere in the middle, the system detects it and instantly routes traffic through the other side of the ring. Boom! Zero downtime.
Section 6. Perfect multi-axis harmony and synchronization. We've covered a ton of deep technical ground today, but this is the climax where it really all comes together into perfect multi-axis harmony. To summarize our deep dive into the architecture, we bypassed the limits of standard Ethernet by using single-frame processing on the fly. We locked our network timing together with 10 nanosecond precision distributed clocks. We separated our continuous and acyclic data using 3-buffer mode for total consistency, and we protected the physical layer with real-time hardware diagnostics. These combined elements are the definitive solution to the microjitter crisis.
You now understand the functional principles that make EtherCAT the gold standard for real-time synchronization between motion controllers and servo drives. The old bottlenecks have been totally eliminated. So I'll leave you with this final thought. How will you leverage nanosecond determinism to push your next machine beyond its theoretical limits? Thanks for joining me on this explainer. Until next time, keep optimizing.
Thanks for watching. Please visit the channel for such more content, and don't forget to subscribe the channel and like if it is helpful to your knowledge, and comment if something is wrong.